Hello. So today, ang gagawin ninyo ay matututong mag-solve ng problems. So you're going to take a look at these exercises that I've prepared and tawag dito, pag-aralan nyo yung solutions dun sa exercises na ito. Okay, so of course, what you're watching now is a video, but you'll also be provided with this solution set in PDF. Okay, but towards the end, kung titignan nyo pagdating dito, you'll have a list of exercises na pwede nyo or na gagawin ninyo actually. And tawag dito, what you're going to do is you select two problems to solve in these in this table, these tables. Okay, you solve them, tapos isulat niyo yung solutions on a sheet of paper, or if you have a mobile device, then you can use your app. Okay, and if you're using a sheet of paper, just take a picture or scan yung paper na yun. And tawag dito, submit yung solutions nyo sa VLE. Of course, it's preferred para nandun lahat ng naka-organize at nandun lahat ng solutions niyo. But at this point, at the time na pinaprepare ko itong lessons na ito, hindi ko pa alam kung kailan magiging available yung VLE kasi binibigay lang nila yun after matapos yung registration. Okay. So, if hindi pa ready yung VLE, we'll send the designated Google Drive folder kung saan dun yung sasubmit yung inyong solutions. Okay? Then, only then, are you going to write your names dito sa table. So, halimbawa, na-solve nyo itong number na ito. So, na-solve nyo na, nakapag-submit na kayo, sa kanilang ilagay yung names ninyo. Okay? So, ganun. Okay. So, what's in it for you? Of course, you were able to practice solving problems. Okay. Secondly, for each problem na masasolve ninyo, I will give 1 point. However, it's 0 or 1. Okay, so you have to give the correct and full solution, otherwise you get 0. Okay? Itong points na to ay add natin dun sa inyong first exam. So you can consider these as bonus points dun sa inyong first exam. Okay? And of course, yung third, siguro na benefit sa inyo dito is, aside from being able to practice solving problems, okay, it may be na dito ako kumuha sa list na ito ng mga problems na isosolve para sa first exam. Now, having said that, ito yung pag-isipan ninyo. If you select problems that are easy, then ang matitira ay yung mga mahihirap na problems. Okay? But if you select problems and solve those problems which are hard, or at least not so easy, then ang matitira sa mga ibang pagpipilian ko ay yung mga mas madadali. Okay, so I would like you to challenge yourself and select yung mga problems na tawag dito medyo challenging para sa inyo, and then submit niyo yung problems na yun. So the deadline is today. Tawag dito, so I'll give you until about 6 p.m. today to submit your solution. Okay, so that's it. And after this, you will start watching yung mga exercises being solved.
Determine the current drain on the battery with no load on the output terminals. And with the 10 kilo ohm load, what is the current from the battery? So the first problem states or asks what the current is if there's no load while the second states that if there's a 10 kilo ohm load, what will be the current drain from the source. So let's consider the case. First, when there's no load, this means that we don't consider the effect of the output voltage, and we simply take the current to be equal to the voltage source divided by the equivalent series resistance. So the current is solved easily by taking 22 volts and dividing it by 10 kilo ohms plus 5.6 kilo ohms plus 2.7 kilo ohms. This gives us a value of 1.2 milliamperes. Okay, and just for completion, let's solve for the output voltage across AB. This is easily solved by taking the sum of the resistances across AB and then multiplying it by the current, which is earlier solved, and this is equal to 9.98 volts. Okay, now factoring in the 10 kilo ohm load across terminals A and B. Okay, so it's 10 kilo ohms. What will be the new current? We see that this becomes a parallel or a network of parallel and series resistors, where RL is parallel to the series resistors R2 and R3. So we have to take the equivalent resistance of this, add it to R1 to get the total resistance. So, and that's how we solve for the current. So the current is equal to the source voltage divided by the equivalent resistance, or the total resistance, which is 10 kilo ohms plus 1 over 5.6 kilo ohms plus 2.7 kilo ohms plus 1 over 10 kilo ohms. Okay, and if we do the math, we get 1.5 milliamperes. Okay, immediately we see that by adding the load resistance, the current increases compared to when there is no load resistance. Now let's take the output voltage, and the output voltage is nothing but the voltage across these 2 points, A and B, which is the equivalent resistance across this network of resistors, and that will give us 1 all over 5.6 kilo ohms plus 2.7 kilo ohms plus 1 over 10 kilo ohms, and multiply that by the current that we already solved. So V out is equal to 6.86 volts. Okay, again, we see that by adding a load resistance which is comparable to R2 and R3, the output voltage decreases significantly. Okay, and this is not something we want, because we want the load to be able to get the proper voltage. Okay, and that load must not affect this voltage, otherwise whatever load you put in here will no longer work effectively. Okay, so that's this is what's called voltage loading. Okay, here are a few more exercises involving circuits with DC sources. Let's try to determine the Thevenin equivalent of these three circuits as seen from terminals A and B. And then for part A, or for figure A, let's determine the value for which maximum power is dissipated. So let's solve part A first. So to solve part A, so what we really want to do is for each of these circuits to be converted into something like this. So RTH and VTH. Okay, And we can solve for VTH and RTH separately. To solve for VTH, we don't involve RL, so we remove RL from this figure and then solve VTH, which is just the voltage across A and B. And then to solve for RTH, we replace the source voltage with a short, or with a with a wire, okay, and obtain the equivalent resistance as seen across terminals A and B. Okay, so to solve for VTH, keeping A and B open, we see that this is a voltage divider equation. R4 doesn't have a voltage. And why is that? Because if these two are open, then there is no current going through R4. There's no current going from this junction towards R4. So all current is passing through R1, R2, and back to R3. Okay, so in this case, we use the voltage divider equation. So the Thevenin voltage is simply equal to R2 over R1 plus R2 plus R3 times 2.5 volts, okay, which is then equal to 78 ohms divided by 100 ohms plus 78 ohms plus 47 ohms times 2.5 volts. So the Thevenin voltage in this circuit is then 0.87 volts. Okay, what about the Thevenin resistance? So to solve for the Thevenin resistance, we replace this DC source with a short. So that's just a wire, which means that 47 ohm resistor and the 100 ohm resistor are in series, and the equivalent series resistance is parallel to R2. Okay, so that means that the resistance as seen through AB is just a series parallel equivalent of R1, R2, and R3. So we can solve for RTH to be 1 over R2 plus 1 over R1 plus R3. Okay, plugging in the values, we have 1 over 78 ohms plus 1 over 100 ohms plus 47 ohms. This gives us a Thevenin resistance of 70 ohms. And to answer this question, this should also be the value of the load resistance in order for the maximum power transferred from the source to the load. Okay, so that's for part A. What about for part B? For part B, again, we do the same. So what we have here, we have a resistor R1, a resistor R2, and a voltage source which is equal to 3 volts. So to solve for the Thevenin voltage, we keep A and B open, so we don't factor in RL. Okay, and then what we have is a 3 volt source which are in series with R1 and R2. So we can actually redraw this circuit to be something like this. 3 volts. Here's your 3 volt circuit. This is your R2, which is equal to 270 ohms. And here we have our R1, which is 100 ohms. And where's point A and B? Point A is here next to the positive terminal of 3 volts, and point B is here next to the intersection between R1 and R2. Okay, so this is point A, this is point B. Okay, perhaps this is now easier to see. If it isn't, we can still redraw the circuit to be like this, so that all the resistors are in the same line. So here's your 3 volts, this is your R2, which is 270 ohms, and this is your R1, which is 100 ohms. This is point B and this is point A. So that's point A right there and point B right here. Now this is probably easier to see, because now we easily recognize the voltage divider, but this time the voltage divider is seen across A and B. So in this case, the Thevenin resistance is derived from the voltage divider across R1. So R1 over R1 plus R2 times 3 volts. So this is equal to R1, which is 100 ohms, R1 100 ohms plus 270 ohms times 3 volts. So VTH is equal to 0.81 volts. Okay, next we solve for the Thevenin resistance. So going back to this circuit, we replace this by a short, okay, or if we go back to this circuit, we replace this by a short. Okay, and we now see that as viewed between A and B, R1 and R2 are parallel to each other. So that means that the Thevenin resistance is just 1 over R1 plus 1 over R2, which is equal to 1 over 100 ohms plus 1 over 270 ohms, so that Thevenin resistance is equal to 73 ohms. Now for part C, to solve for the Thevenin voltage, we ignore the load resistance across A and B. Okay, and this is actually already familiar to you because we've already solved this type of problem in the previous example. So the Thevenin voltage is easily solved using the voltage divider equation across R2. So the Thevenin voltage in that case is R2 over R1 plus R2 times 1.5 volts equal to 56 kilo ohms divided by 100 kilo ohm plus 56 kilo ohms times 1.5 volts. So the Thevenin voltage in that case is 0.54 volts. For the Thevenin resistance, we replace the source voltage with the short, which means that as seen across A and B, R1 and R2 are parallel to each other, so that the Thevenin resistance is nothing but 1 over R1 plus 1 over R2 is equal to 1 over 56 kilo ohms plus 1 over 100 kilo ohms, and the Thevenin resistance is equal to 36 kilo ohms. Let's next reduce this circuit to its Thevenin equivalent as viewed from terminals A and B. Then afterwards, let's determine the value of the load resistor connected between terminals A and B for maximum power transfer to the load resistor. So we want to convert this circuit to its Thevenin equivalent, okay, which can be seen as this. So this will be your Thevenin voltage, and this is your Thevenin resistance. And according to the maximum power transfer theorem, okay, the load resistance required to have maximum power transferred to the load should be the case when the load resistance here is equal to the resistance here. That means that to answer the second question, the load resistance must be equal to the Thevenin resistance. So we only need to solve for the Thevenin resistance to get the answer to the second part of this problem. So let's try to solve first for the Thevenin voltage. Okay, to solve for the Thevenin voltage, we keep these two terminals open. And that means that we want to solve the voltage across A and B, which is nothing but the voltage across R2. And you notice that this is a voltage divider. Okay, so which means that the Thevenin voltage can be solved using the voltage divider equation. R2 over R1 plus R2 times 15 volts, okay, which is then equal to 22 kilo ohms divided by 100 kilo ohms plus 22 kilo ohms times 15 volts. And this gives us 2.7 volts. So this is equal to 2.7 volts. The Thevenin resistance is solved by shorting this source voltage. So that means that this is just a wire here. So replace the source voltage by wire. And this means that as viewed from terminals A and B, R2 is in parallel with R1. That means that RTH can be solved by simply taking the equivalent resistance of R1 and R2. So 1 over R1 plus 1 over R2, and take the inverse of that. So 1 over 22 kilo ohms plus 1 over 100 kilo ohms, and take the inverse of that, so that the Thevenin resistance is 18 kilo ohms. So this is 18 kilo ohms. And to answer the second question, the load resistance must also be 18 kilo ohms in order for the maximum power to be transferred from the source to the load across A and B. Okay, the next problem involves a Wheatstone bridge problem. Okay, so bridge network is shown. To what value must RV be set in order to balance the bridge? The condition when the bridge is balanced is that the voltage across AB is 0, and this means that we have to satisfy this condition where the ratio R1 and RV must be equal to the ratio R2 and R3. Okay, immediately we can solve for RV to be equal to R1 times R3 divided by R2, and R1 is 390 ohms, R3 is 560 ohms divided by R2, which is 1 kilo ohm, so that RV must be set at 218 ohms. Okay, so this should be 218 ohms. Okay, determine the output voltage of the unbalanced bridge for a temperature of 65 degrees Celsius. The thermistor has a nominal resistance of 1 kilo ohm at 25 degrees Celsius and a positive temperature coefficient. Assume that its resistance changes 5 ohms for each degree change in temperature. So we want to find out the voltage across AB, which is defined as the voltage at point A minus the voltage at point B at 65 degrees Celsius. Okay. At 25 degrees Celsius, the resistance across the thermistor, which is R1, is 1 kilo ohm. Notice that if this is 1 kilo ohm, this is also 1 kilo ohm, this is 1 kilo ohm, this is 1 kilo ohm. This means that the bridge is balanced, so since all resistances are the same. That's another given value, which is not immediately seen in the problem. A positive temperature coefficient means that the thermistor changes positively, or the thermistor resistance changes positively with increasing temperature. And another type of thermistor is a negative temperature coefficient thermistor, wherein there's a negative change in resistance as the temperature increases. So in this case, for every degree change, we have a 5 ohm increase, which gives us the value of R1, or the change in R1. Okay, so if if the temperature is 65 degrees Celsius and we compare that to 25 degrees Celsius, that's a 40-degree change. That means that R1 changed by, okay, so 5 ohm per degree, multiply that by 40 degrees Celsius. So R1 changed by 200 ohms. This means that R1, okay, is equal to 1.2 kilo ohms at 65 degrees Celsius. Okay? Okay. Now we can solve for VAB. Okay, but first we need to know what VA is and what VB is. VA is the voltage at this point relative to the ground, and VB is the voltage at this point relative to ground. Okay, if we take a closer look, this line here is a voltage divider. You have the source there, 9 volts. You have one resistor here, R1, and another resistor here, R3. Also, this series resistor here is also a voltage divider, where you have the 9 volt source, the R2, and your R4 resistances. Okay, so we can easily solve for the voltage at point A and voltage at point. So we can easily solve for the voltage at point A and voltage at point B. Okay, so the voltage at point A is therefore given by, using the voltage divider equation, 1 kilo ohm divided by 1.2 kilo ohm, which is the thermistor resistance, plus 1 kilo ohm multiplied by 9 volts. So that's 4.09 volts. VB is easily solved to be 1 kilo ohm divided by 1 kilo ohm plus 1 kilo ohm times 9 volts, which gives us 4.5 volts. That means that VAB is equal to 4.90 volts minus 4.5 volts. Okay, and this will give us negative 0.41 volts. So if you have a multimeter and you put your multimeter electrodes here and the temperature is 65 degrees, you should expect an output voltage of negative 0.41 volts. Okay, now here is an exercise on the utilization of the superposition theorem. And the idea is we want to calculate the current in the rightmost branch, which means that we want to solve for the current through the resistor R5. In order to do that, we use the superposition theorem, which states that the current in any given branch of a multiple source linear circuit can be found by determining the currents in that particular branch produced by each source acting alone, with all other sources replaced by their internal resistances. This means that if we want to calculate the current through R5, we need to replace the 2 volt source with its internal resistance and then solve for the current R5, and then replace the 3 volt source with its internal resistance and then solve again for this new current R5. Then we add those two currents together, which was obtained from 2 different approaches. That's what superposition theorem states. In this circuit, there is no internal resistance for the voltage sources. This means that we can simply replace each of the voltage source by a short. So let's solve this problem by first replacing the 3 volt source with a short. In other words, we ignore that and then replace that with a short. Okay, this means that in order to solve for the current R5, we need to first simplify this equivalent parallel resistance, and let's call that R6. And then we need to solve for this equivalent resistance, okay, which we will call R7. And then we solve for this equivalent resistance, which we call R8. And then finally obtain the total resistance, which we now call R9. From there, we can solve for the currents. Let's solve for R6 first. R6 is equal to 1 over 1 kilo ohm plus 1 over 2.2 kilo ohm. And that is given by 0.69 kilo ohms. Okay. Next, we need to solve for R7. R7, this orange box here, is the series resistance of R3 and R6. So R3 plus R6. So that gives us value of 1.69 kilo ohms. Now R8 is the equivalent parallel resistance of R2 and R7. So that's 1 over 1 all over 2.2 kilo ohms plus 1 over 1.69 kilo ohms. This gives us 0.96 kilo ohms. And then R9 is nothing but R1 plus R8. Okay, so that's 1.96 kilo ohms. R9 is the equivalent resistance of the whole network of resistors. This means that the current I1 is equal to 2 volts divided by R9. So that's 2 volts divided by 1.96 kilo ohms. And that's 1.02 milliamperes. Okay, so I1 is the current passing through R1 and the current passing through R8. Now that current passes through this junction and separates to R2 and then to R7. To solve for R2, we need to determine the voltage across R2. The voltage across R2 is V2. But we see that here's the source, here's R1, and this is V2. So that's a voltage divider equation. So that's R8 divided by R1 plus R8 times 2 volts. Replacing these values, R8 is 0.96 kilo ohms divided by R1 plus R8 is 1.96 kilo ohms times 2 volts. So V2 is equal to 0.98 volts, which means that the current through I2 is equal to V2 divided by R2, which is equal to 0.98 volts divided by 2.2 kilo ohms, or I2 is equal to 0.44 milliamperes. So we have 0.4 milliamperes going through here. So we have 1.4 milliamperes going through here and then 0.44 milliamperes going through here. The rest is going to R7. So the current through R7 is 1.04 milliamperes minus 0.44 milliamperes. So that's 0.60 milliamperes. Okay, and that's also the current going through R3 just before it's separated across that junction. So that means that the current through I3 is 0.60 milliamperes. Okay, so what about the current through R4 and the current through R5, which ultimately we want to solve? 0.6 milliamperes passes through R3, and that's separated at this junction here, and it goes through R4 and R5. So in order to solve for the current through R4 and R5, well, we only want to solve the current through R5, we need the voltage across these two junctions here. And to solve for the voltage across these two junctions, we see that it's again a voltage divider equation from R3 to here, okay, where you consider this as the source voltage. We already know what this voltage is. That's the voltage across R2, which is 0.98 volts. So all we need to do to solve for R5 is first to solve for the voltage across this junction. The voltage across that junction, let's call that V5, is equal to the equivalent resistance R6 divided by R3 plus R6. Sorry, multiply that by 0.98 volts, which is the voltage across these two junctions. R6 is 0.69 kilo ohms and R3 is 1 kilo ohm. So this means that V5 is equal to 0.40 volts. So that means that the voltage across these two junctions is 0.40 volts. Now we can solve for I5 because we know that there's 0.4 volts here. So I5 is equal to 0.4 volts divided by 2.2 kilo ohms. This means that we have 0.18 milliamperes. Okay, so that's when we short the 3 volt power source. Now to solve for the current when the 2 volt source is shorted, we see in this case that R1 is parallel to R2, and that's going to be our R6. Then we see that R6 is in series with R3, and that will be our R7. Next, R7 is in parallel with R4. And now we come to a point where we figure out what is the correct circuit here. So if we redraw this, we have our R7 like this. Then we have R4 in series with our source voltage, in series with our source R4 in series with our source voltage are 3 volts, then R5. Okay, how do we redraw this? So first let's draw the 3 volt voltage, source voltage, like so. Then we know that it's connected to R4, like so. And then there's a junction that connects to R5 and R7. Now R5, the other end of R5 is connected to the negative terminal of 3 volt source. And also the other end of R7 is also connected to the negative terminal of 3 volt source. So this is what it looks like. So the next step would be to simplify R5 and R7. This is going to be our R8. Finally, we have our R9, which is just the sum of R4 and R8. Okay, so now that we have that figured out, let's then solve for R9. The first thing we need to solve is R6. So R6 will be equal to 1 over 1 kilo ohm plus 1 over 2.2 kilo ohms. And that will give us 0.69 kilo ohms. Next we solve for R7. R7 is equal to R6 plus R3 because they are in series. Okay, Since R3 is 1 kilo ohm, this will be 1.69 kilo ohm. And then R8, as we see from here, is a parallel combination of R5 and R7. So that's R8 equals 1 over 2.2 kilo ohms plus 1 over 1.69 kilo ohms, and that will give us 0.96 kilo ohms. Okay, and then finally R9. Okay, we'll put R9 here. It's just R4 plus R8. Okay, which means that since R4 is 1 kilo ohm, this will be 1.96 kilo ohms. Okay, it's a bit familiar. Okay, and that's because the circuit is actually symmetric. Okay, about this. Okay, of course I could have started with that, but it's easier like this, especially if you're applying the superposition theorem first. Okay, so now that we have that, we can now solve for the current going through R4 and R8. So the current going through R4 and R8 is 3 volts divided by R4 plus R8. Let's call that I4. So that I4 is equal to 3 volts divided by R4 plus R8, and 3 volts divided by 1 kilo ohm plus 0.96 kilo ohms. So that I4 is equal to 1.53 milliamperes. So this is the current passing through R4. So that's 1.53 milliamperes, but it's also the same current passing through R8. And that current separates into two currents, I5 and I7 here. Now to solve for I5, which we are really after, we just need to get the voltage across this junction here. And to do that, we recognize that this is another voltage divider. To get V5, let's call that V5, we equate that to R5 divided by R4 plus R5 times 3/4. So V5 is equal to R5 divided by R4 plus R5. R5 is 2.2 kilo ohms. R4 is 1 kilo ohm plus 2.2 kilo ohms times 3 volts. And that will give us 2.06 volts. Okay. So the voltage across this junction is 2.06 volts. And if we divide that by R5, it will give us I5. So V5 divided by R5, 2.06 volts divided by 2.2 kilo ohms, which results to a current of 0.94 milliamperes. And that is if 2 volts was shorted. So according to the superposition principle, the total current through I5 is 0.18 milliamperes plus 0.94 milliamperes, which is equal to 1.12 milliamperes. Okay, so that's how we use the superposition theorem.